Hello and welcome to a new video in a course on calculus. In the previous video, we defined infinite series and we've talked about some examples of infinite series. The purpose of this video and the coming few videos is to touch base on some convergence tests that for infinite series. I remind you, we started by defining a series to be the sum from n equals 1 to infinity of the terms of some sequence an. So this is the definition of an infinite series, right? So whether or not this series is convergent, that's a separate question. And we defined convergence of a series in the following way. So we said this series is convergent if the nth partial sum, or let me just say if the limit of the nth partial sum Sn, which is equal to, let me just say S sub big N from n equals 1 to n of a sub n exists. So if this limit exists, then we say that the series is convergent, and the value to which this sequence converges is going to be the value of the series. In other words, the limit of Sn as n tends to infinity, let's say this is L, we say that the sum of an from n equals 1 to infinity is equal to L. Okay? So this is the definition of a convergence. So this is the definition of convergence of series. If the partial sum converges, then if the sequence of partial sum converges to a limit L, then the series is convergent and its value is L. So I've been stressing in the previous video, I've been stressing this point that a series is a limit. So please guys, whenever you're adding series, whenever you're doing any arithmetic with series, you should be careful that the limit should exist. Because if the limit does not exist, pretty much all arithmetic you do is dangerous. Like you might be subtracting infinities, for example, and you should be careful when you work with series that are divergent, which is the opposite term of convergent. So a series is divergent if it's not convergent. So this definition we made the previous video. And the purpose of this video is to go over the nth term test and the comparison test. So we'll be going over these, and in the coming videos we'll be covering more convergence tests, right? So you're given a series, sum of an from n equals 1 to infinity, and you want to decide whether or not this is a convergent series. You want to decide whether or not this is equal to a number, or it's just something that doesn't exist, or it's equal to infinity. So the first theorem we're gonna learn is called the nth term test, and the nth term test says the following: if the limit of an as n tends to infinity is not zero, if the limit of the summand is not equal to zero, then the series diverges, right? So I want to here stress something, because a lot of students do this mistake that they apply it in the opposite way and they apply it wrongly. So let me just before I give you this example, let me just state the theorem in two different ways. So the theorem can be stated in two different ways. The first way is that the sum of an from n equals 1 to infinity converges. If that happens, then an, the limit of an as n tends to infinity, is equal to 0. Okay, and the other way to state the theorem is as mentioned above: if the limit of an as n tends to infinity is not equal to 0, then the sum of an from n equals 1 to infinity diverges. So this is called the counter positive of the above statement, right? So I want you to be careful here. I'm not saying that if the limit of an is 0, then the sum is convergent. This is not what I'm saying. I'm saying if it is convergent, then it's necessary that the summand goes to zero, right? So if the summand doesn't go to zero, it must be that the series is divergent. However, it's not true generally. In general, it's not true that if that the limit of an as n tends to infinity equal to 0 implies the sum of n equals 1 to infinity convergent. So this implication, or this if then statement, is not true in general. So you can't tell me I have a series, it's convergent because the limit of its summand is 0. This is not true. This theorem is saying if the sequence is, if this series is convergent, then the summand must go to 0. So you can only use this theorem to prove a series is divergent, right? So the first thing you need to do when you have a series and you're asked to decide whether it converges or not is to compute the limit of its summand. If the limit is 0, this should give you some, this should make you this should give you some hope that the series is convergent, but it's not a proof, right? It's not enough to claim that it's actually a convergent series. However, you can use this theorem to prove that a series is divergent. If you have a series that is divergent, if you get the limit of the summand and it's not 0, then you can say for sure that the series is divergent. This is the point I wanted to make, right? So let's take as an example, let's take this sequence, let's take this sequence, and correspondingly we have this series, right? So if you compute the limit of an, which is this thing, as n tends to infinity, this is the limit of 1 plus 1 over n as n tends to infinity. Now the limit of 1 is 1, and the limit of 1 over n is 0. This is something we did in previous videos, and this is equal to 1, right? But 1 is not 0, thus the limit of the summand is not 0. Now, applying the theorem that we have, if the limit of the summand is not 0, then we know for sure that the series is divergent. So this series is divergent because the limit of the summand is not 0, right? However, since I mentioned this warning here, for you, let me just give you an example that proves what I just told you. So let me just show you this example. For example, if you take the sum of 1 over n from n equals 1 to infinity, this is something that we're gonna prove in a coming video. This series is divergent. Like, this series is divergent. We're gonna prove this in the coming video, right? However, if you look at the limit of 1 over n as n tends to infinity, you see that this limit is 0. But this is not enough to show that the series is convergent, because as I just told you, this series is actually divergent. We're gonna prove this in a coming video. However, you see that the summand does go to 0. So this is not a test of whether this is not a test of convergence, right? So yeah, this is something that I wanted to stress, and that's it, I guess. So for example, you just now know, if you look at the series sum of 1 from n equals 1 to infinity of n, yeah, I guess there are important examples there are important things to conclude from this theorem. So let us go over a few important examples. For example, if you look at the sum from n equals 1 to infinity of n, right, your sequence, your summand here is just n. So you're summing 1 plus 2 plus 3 plus 4, and you're doing this up to infinity, right? So as you see, you expect that this sum is not convergent, right? Because you're kind of adding bigger and bigger numbers, so it's kind of going to infinity, right? So and the way you can prove this is that you take the limit of from n equals 1, like you take the limit of this command as n tends to infinity, and you see that this limit is infinity, right? We know that this limit is infinity, but infinity is not equal to 0, and thus by the nth term test we know that this series is divergent. So this series is actually divergent, right? So let's take another example here. So these are kind of quick and easy checks of divergence of a series. So if you look at the series minus 1 to the n, from n equals 1 to infinity, right? So this series is the sum of the terms minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, and so on. We can already prove this, that this sequence is divergent using the definition of convergence and divergence, i.e. using the fact, i.e. we can already prove this using the nth, by considering the partial sum. So if you consider the partial sum, for example, s sub big N from n equals 1 to n, right, of minus 1 to the n, you see that if we add even number of terms, like if you add 2 terms, you get 0. If you add 4 terms, you get 0, right? So every time you add even number of terms, you get 0, because every minus 1 and 1 will cancel with each other. So this is 0 if n is even. However, if you add odd number of terms, like if you add 1, 2, 3 of these, you see that you get for example here, you get negative 1, because like these will cancel and this will stay. So you see, you get negative 1 if you add 3 terms. If you add 5 terms, for example, you also get negative 1, because these will cancel and these will cancel and be left with this negative 1, and so on. If n is odd, you get a negative 1. Now thus if you want to consider the limit of Sn as n tends to infinity, you see that you cannot determine, right? You cannot determine what the limit is, because like if n is getting bigger, it can be getting bigger as an even number or as an odd number. Thus this limit does not exist, right? We know for sure that this limit does not exist, right? So since the limit does not exist, we know that that Sn is divergent. But if Sn is divergent, then the series is divergent, because this is how we define the convergence and divergence of this series. So we do know for sure that this series is divergent. However, there's another way to go around this and see this. So why is this series divergent by the nth term test? Is that clear? Well, it is, because minus 1 to the n, if you look at this is the summand. If it doesn't go to 0, then the series cannot be convergent by the nth term test, right? So the limit of this, if you look at the limit of this as n tends to infinity, what is that? Well, for sure this cannot be 0, right? So this can be so this limit, we know that this limit does not exist, because it's the limit as n tends to infinity of 1 if n is even, and if of negative 1 if n is odd, right? So in this case, we know that this limit does not exist. But since the limit does not exist, it means that the limit is not 0, right? So since the limit is not 0, then we know for sure that this is divergent, right? So so this is another way to see this by the nth term test. So this series is divergent also. You can see this by the nth term test. Alright, so let us recap now what we have so far. So far we have to check convergence of the series of a series, let's say sum of an from n equals 1 to infinity, show that the nth partial sum is convergent. Because remember, a series is just a limit, and it's a limit of Sn as n tends to infinity. So if you check that this limit exists, then you know that this sequence, this series is convergent. So so far, this is the only tool we have to prove that a series is convergent. Now, so these are the tools that we have. Now for divergence, we have the to show a series is divergent. So let's say it's a series an from n equals 1 to infinity. To show that a series is divergent, you have the first tool is show that the limit as n tends to infinity, as big N tends to infinity, of Sn, the partial sum. I remind you, the partial sum, it's the sum from n equals 1 to n of an. This is the partial sum. Show that this does not exist, right? Or it's equal to infinity. So this is one tool you have for divergence. The other tool that we just learned is the nth term test. Show the limit of the summand an, right? Show this limit is not 0. If you show that this limit is not 0, then the series for sure diverges by the nth term test. So these are the tools we have so far, and let us learn more tools. Okay, so the next tool we're gonna learn is what's so-called the comparison test. So quite often you will see you will encounter series that look similar to other series that you know is convergent. For example, we know that a geometric series that we studied in the previous video, that are of the form the sum of r to the n from n equals 0 to infinity, these are convergent for r an absolute value less than 1. So we do know that, right? So this is something that we know. Now, if you take a sequence, if you take a series that looks similar to this, and you have an inequality, you have a kind of inequality between the terms, then this should tell you something about the convergence. So let me just give you an example here, before we state this, let me just tell you where you might see this. So let's say, for example, we know that the sum of 1 over 2 to the n, as n goes from 0 to infinity, this is convergent because, so remember, this is a geometric series, right? This series is convergent because it is a geometric series with r equals 1 over 2 and a equals 1. Because remember, 1 over 2 to the n can be rewritten as 1 over 2, all of it to the n, and you have a 1 outside. So if you look at this form here, this is r equals half and a equals 1, right? So r equals half, it's less than 1. So since it's less than 1, and it's actually a positive number less than 1, then you know by the geometric series convergence that we proved last time that this is convergent. So we know that this is convergent, right? So now suppose you found something similar. You encountered a similar series. For example, you encountered the series, the sum from n equals 0 to infinity of 1 over so let's say 2 to the n plus 1, right? So this is not a geometric series. right? It's different from this form, like, because it's not it's not like of the form r to the n. You can't write this as in the form of r to the n, right? So this is, but this looks similar to a geometric series. This is close to a geometric series. So you have some hope that this is convergent because it's similar to this geometric series. But how can you use that? How can you prove that? So here's what the comparison test is telling you. Since you're comparing these two and they look similar, you have the following. We know that 2n plus 1, this is bigger than 2n, and this is true for every n. This is true for every n. Okay. And now if you take the reciprocal of this, if you take the reciprocal, you change the identity, you change the comparison sign. So it's going to be less than 1 over 2 to the n. So what the comparison test is telling you, if you know for sure, so this is for every n, if you know for sure that the summand that you have for your series is less than the summand of a series that you know is convergent, right? For example, this series we know is convergent, and we know that this summand that we have is less than the summand of the other series that is convergent, then we know for sure then the sum of 1 over 2 to the n plus 1 is convergent by comparison test. Right? So it's kind of quote unquote telling you that you can sum both sides of the inequalities, and thus since the right hand side is less than infinity, then the left hand side will be less than infinity. Okay, so this is what I wanted to tell you. This is the example. So this is the idea of the comparison test. Let me state it in a mathematical general form. So if you have a series sum of an and you have a series sum of bn, okay, and you know that both of the ans and the bn's are positive, are non-negative, and you know that an is less than the bn, right? You know for sure that an is less than bn, right? And I want to stress here that this is very important. It's very important that they are both non-negative, okay? If that's the case, and if it's also the case that the sum of the bn's is convergent, like the sum of these is convergent, the sum of the one that is bigger is convergent, just as in this case where the sum of this is convergent, then the sum of an is convergent, right? Then you know for sure that this series is convergent. And this is very helpful. Now, before I give you another example, let me just stress how important this thing is, right? Let me stress how important this thing is. So consider the set, for example, the sum of -1 from n equals 1 to infinity, and the sum of 1 over 2 to the n from n equals 1 to infinity, okay, or 0 to infinity. Okay, so let's take 0 here. So we know for sure, that -1 is less than 1 over 2 to the n. So this is always true because this is a negative number and this is a positive number, right? So this we know for sure. However, though this is convergent by the geometric series r equals half, so this is a geometric series r equals half, and thus this is convergent, we do not, this thing is not convergent. Like if you sum -1 infinitely many times, you will get negative infinity, right? So you know for sure that this thing is not convergent, though we have this inequality. So what went wrong? Is the theorem that we're saying wrong? Well, no. What went wrong is that you don't have the fact that they're both non-negative. They're both positive numbers, right? It should be that this is positive and this is positive and this inequality holds, right? But this is not the case here because this is negative. So even though we have the assumptions of the theorem, you don't have the fact that they're both positive, and thus you cannot apply this theorem, right? So it's important that the summands are actually non-negative, and this is happening for every n. So this is very important. So let's take a quick another example. Let's take another example here, just to reapply the theorem. If you take the sum of 1 over 3, 3 to the n plus 2 to the n from n equals 0 to infinity. If you take this, right, so this resembles, it looks like a geometric series 1 over 3 to the n or 1 over 2 to the n. So it looks like this, right? So this looks like this. So you're kind of feeling that this should converge, right? Because you know that this is a geometric series with r equal 1 over 3, because this thing is equal to 1 over 3 to the n, right? So you know that this is a geometric series with r equals 1 over 3, and 1 over 3 is less than 1. It's also positive, and thus this series is convergent. So you know that this is convergent, but this is not of this form. Like, this is not the case. How can we claim, or how can we show that this is actually convergent? Before we do that, before we check that this is convergent, let's try to make ourselves feel better about this and try the nth term test. So let's try the nth term test to see if this limit is 0, because if this limit is not 0, we know by the nth term test that this is divergent, right? However, if the limit is 0, it doesn't tell us anything, right? So what is the limit of this? Well, this is the limit of if you put an infinity here, it's going to be 3 to the infinity, which is infinity, plus 2 to the infinity, which is infinity, and this is 1 over infinity, and this is 0, right? So the limit is actually 0, so this should make you feel better about the possibility of convergence, but it doesn't tell you, it doesn't guarantee you convergence, right? How can we prove convergence? How can we show convergence here? Well, we're going to use the comparison test again. So we know that 1 over 3 to the n plus 2 to the n. The first thing we know about this is that it's always bigger than 0, right? This is always the case, and this is very important. Part of the assumption for the theorem. It has to be that they're bigger than 0, and we have this inequality, right? It's bn should be bigger than an, and it should be that the sum of the bn's converge, right? To get that the sum of the an's converge. So in this case, we have that this is first of all non-negative, and second, it's less than 1 over 3 to the n. So let me show you why this is the case. Well, 3 to the n plus 2 to the n is bigger than 2 to the n, bigger than 3 to the n, or 2 to the n, doesn't matter. So if you look at this, why is that the case? Well, this is the case because this is actually always positive. But since this is always positive, then 3 to the n plus a positive number is certainly bigger than 3 to the n. And this is for every n. And if you take the reciprocal of these, you change this inequality, and you get this inequality. And this is happening for every n. And this is another important thing for you to note. It should happen for every n. Okay? So we have this inequality. So since the sum of 1 over 3 to the n, just as we argued here, because it's a geometric series, since this is from n equals 0 to infinity, since this is convergent, then by the comparison test, we know that the sum of this thing plus 2 to the n, as n goes from 0 to infinity, is convergent. You see how cool? So now as long as you can find an inequality, as long as your summand is positive, and you can find an inequality with the summand of a convergent series, you can get convergence for free. Okay. So this is the second tool that we learned. So let us add this to our list of tools for convergence that we have. So the first thing is to show. So the first tool we know. So let's enumerate this. So the first tool for convergence that we said we have is that we want to prove that the limit of the partial sum converges, and the second tool is the comparison test. Right, so this is the new tool that we're using here. This is the new tool that we have, and it's this thing.